Hi, this is Kevin Trainer. Welcome to part two of my lecture on chapter 11 of the Zelle 3rd edition Python programming book. Part one was about the kind of data collections we call lists, and part two is about the kind of data collections we call dictionaries in Python. So after list, the dictionary is probably the most widely used collection data type in Python. Dictionaries are not as common in certain other programming languages as lists. So let's go to the next slide. So let's talk about some of the basics, okay? Lists allow us to store and retrieve items from sequential collections. When we want to access an item, we look it up by index, its position in the collection. What if we wanted to look students up by student ID number? In programming, this approach is called a key-value pair. Okay, so what we would like to do is we would like to provide a key, like student ID number, and what we would like to get back is a value, like a student object. So we access the value, the student information associated with a particular key, student ID. There are lots of examples. Names and phone numbers, usernames and passwords, state names and capitals. Anything you'd want to do a lookup on. And that's why the name for this particular data structure, I think, was well chosen. Because for common people, what do they look up? Well, they look up kind of words in a dictionary, right? So we look up the word, we find the word, and we get the definition, okay? Key value. So a collection that allows us to look up information associated with arbitrary keys is called a mapping. That's a computer science term. Python dictionaries are an example of a mapping. Other languages call them other things like hashes or associative arrays. In Python, these mappings are called dictionaries. Dictionaries can be created in Python by listing key-value pairs inside of curly braces. That's how we can hard code a dictionary. Keys and values are joined by a colon, and they are separated with commas. Okay, so let's look. Here we have a dictionary called password. That's because we didn't have the characters to type password, apparently. And so the whole dictionary is surrounded by these curly braces, and it's got 3 entries, okay? And each of the entries is key, colon, value. And then there's a comma, then there's the next entry, key, colon, value. And then a comma, and then the third one, key, colon, value. If either the key or the value is a string, we're going to surround it by quotes or apostrophes. Okay? If a key or a value were an int, we could just code the int right there as a literal int. So we use an indexing notation to do the lookups in the dictionary. So if in fact we ask for the name of the dictionary, password, and we pass it this index expression, Guido, that's the key value, Then we'll get back the value. Okay, so the key is Guido, and what do we retrieve? The value, super programmer. Now, Guido is a reference to Guido van Rossum, who is the father of Python. Okay. So if we have the name of the dictionary and then square brackets and a key value, it returns the object with the associated key. Dictionaries are mutable. Oh, this is great. Now we have a second kind of thing that is mutable. The lists were mutable. We proved that. Well, dictionaries are as well. Okay. So if we want to change the value of the entry in the dictionary associated with the key Bill to blue screen, which is a Microsoft Windows joke, because Bill is for Bill Gates. Okay. We are actually going to replace whatever the value object was for Bill. So let's go back and look and see what it was. I think it was Monopoly. Okay. So we had three entries, Guido, Turing, and Bill. And the value for Bill was Monopoly. And after we execute this statement here, the value for Bill is replaced with blue screen. Okay? So the result is Guido, super programmer, Bill, blue screen, Turing, genius. Did you notice that the dictionary printed out in a different order than it was created? Yeah, I did. How about you? Well, let's find out about that. Mappings are inherently unordered, so they don't have a reliable order. Okay? If we're interested in some kind of orderly presentation of the data that we have in a dictionary, then we have to do further processing on it to get it into order. Okay? Its natural state is to be unordered. Internally, Python stores dictionaries in a way that makes the key lookup very efficient. When a dictionary is printed out, the order of the keys will look essentially random. If you want to keep a collection in a certain order, you need a sequence, not a mapping. So you need another kind of collection. You need a list. Okay? So dictionaries are good for data that we want to access one entry at a time by its key value. We can, if we want, by doing some further processing, we can present that data in an ordered way, but that's not the natural presentation of the data that's in a dictionary. So each entry is a key value pair. Keys can be any immutable type. Values can be any type, including programmer defined. So this is an important part. The key part has to be some immutable type. What are the immutable types that we know? Well, we know about ints, we know about floats, we know about strings, we know about booleans. Okay? Those can all serve as the key part. What can the value types be? Well, they can be any immutable type or any mutable type. Okay? So, including a programmer defined. So, with a custom class. Now, the only custom class we've seen so far is student. Okay? So, we could have a dictionary of students. Okay? We'd have to pick what we want the key to be. It might be the student ID or it might be the name. And what would be the value? Well, it could be a student object. Okay, that is a mutable object. All right, let's see some more. Like lists, Python dictionaries support a number of handy built-in operations. A common method for building dictionaries is to start with an empty dictionary and to add the key value pairs one at a time. Okay, so what are we doing here? Well, it looks like here that we're reading passwords from a file called passwords. And so we are, for line in open, passwords for reading. Then we're going to read a line at a time. We're going to split the line into user and pass. And then what are we going to do? Well, we're going to say that the dictionary called password, we're saying that in the entry for the key user, we want to store the value pass. Okay. I don't think I have to tell you that I think that these are all variable names that are too short and not sufficiently descriptive. Okay, well, let's look at what some of these operations are. Well, we can actually we can ask the question, is a particular key in the dictionary? Okay, and we get a Boolean answer, true or false. We can call on the dictionary, we can call the method keys, and it returns a sequence of keys. So we'll get the keys in a list. Okay. We can also ask for the values. So what do we get? Well, we get the values in a list. Okay, so when we get the keys, where are the values? They're still in the dictionary. We didn't get them. When we get the values, where are the keys? They're still in the dictionary. We didn't retrieve them either. We just either get a list of keys or a list of values. If we ask for items, we get key value pairs. Now, one of the things we haven't covered too extensively is this idea of a tuple. A tuple is a very simple data structure that holds more than one value. So it's a relation of several values. So when we ask for items, we get a list of key value pairs. And each of those key value pairs is called a tuple. We'll see an example in a couple of slides. If we say that we want to del or delete, and then we say the dictionary key, we delete that entry. When we mean entry, we mean the key value pair. So the key's gone, the value's gone, it's all gone. Okay? If we say we want to clear the dictionary, we wipe out all the entries. Okay? If we want to loop through the keys in the dictionary, we can say for var in dict, that's going to give us the keys one after the other. Okay? And we can get a value from the dictionary by calling a get on the dictionary, okay, and providing a key and a default value, and we'll explain this in a slide or two. Okay, so this is how we get values out of the dictionary. It's a lookup. Okay. because dictionaries are good data structures for applications where we need to do a lookup. And we're going to explore a couple of those applications in the next couple of slides. Okay, so if we call the keys method on the password dictionary, we get the key values: Guido, Turing, and Bill. If we say that we want to create a list of password values, we get a list of the values: super programmer, genius, blue screen. If we say that we want a list of the password items, well, each item is a key value pair. This is how we show a tuple. We show a tuple as two or more values surrounded by parens, okay? And the values are separated by commas. So this is a tuple that has two strings, key string, value string, separated by a comma, okay? So this is the first a tuple is the pair Guido, super programmer. The second tuple that's in the list is the key value pair Turing, genius. And then the third tuple is the key value pair Bill, blue screen. Okay, we can ask Bill in password, true. We can ask Fred in password, false. We can say password get Bill unknown. We can say password get Fred unknown. What's this unknown stuff? Well, when we do a get, we don't always know if, in fact, the key that we're looking for is going to be there, right? We could be asking for a key that just isn't in the dictionary. There's no entry with that key. So what value are we going to get back? Well, it turns out that there's a really kind of sweet version of how you get things, where you say that you want to get, and you give it the key, and then you say, oh, this is the value that I want to use if you don't find an entry with that key. So here, when we say password get Bill unknown, it turns out the Bill actually has an entry in the dictionary, so we retrieve the value, blue screen. That's how we get that. When we do a get for Fred, there is no entry, and so we assign the value unknown. So we get unknown. If we say that we want to clear the dictionary password, then when we ask for a password, we get an empty dictionary because we cleared it. So we're going to find an application for this. There are so many applications of this, but this is a pretty classic application of what to do with dictionaries, okay? We're going to write a program that analyzes text documents and counts how many times each word appears in the document. This kind of document is sometimes used as a crude measure of the style. The style similarity between two documents. And it's used by automatic indexing and archiving programs. So people, when they write, they have a particular writing style. And a really crude way to come up with a metric of that style is just to look at the frequency of their word use. Different people have kind of word favorites that they tend to go back to. Okay, so that's what we're going to do. All right. So this is a multi-accumulator problem. Okay, what we want is we want to have an accumulator for each word that appears in the text. So if it appears once, well, we're going to have a total occurrences for that frequency, as we call it, of 1. Okay, if it occurs 10 times, and we want to have the value 10 when we're done. So we need to count for each word that appears in the document. We can use a loop that iterates over each word in the document, incrementing the appropriate accumulator. The catch: we may possibly need hundreds or thousands of accumulators. So we definitely don't want to have to create a variable for every imaginable word that we could find. That's not really feasible. So it turns out that dictionaries are just a sweet way to solve this need. So let's use a dictionary where strings representing the words are the keys, and the values are ints that count up how many times each word appears. To update the count for a particular word, W, we need something like this. It counts index W equals count index W plus 1. We're going to bump it up by 1. Okay, well that's pretty good. We've done a lot of counting like this. Okay, and again, the counting pattern is kind of a special trivial case of the accumulator pattern. Okay, now here's a problem. It's going to be different the first time we encounter a word because it won't be in the dictionary. So when we go to look in counts for that particular word, it's not going to be found. Okay, well, we can use that to our advantage, provided that we're expecting it. So if we weren't going to take advantage of the special way that get works, we would take this kind of approach. If W is already in counts, add 1 to the count for W. Else, set the count for W to 1. Oh, okay, this is kind of the pseudocode for this. Okay. So let's take a look at the code alternatives. Okay, so the kind of straightforward code alternative says this: if if the word is in counts index W equals counts index W plus 1. We're going to bump up the count by 1. Else, counts W equal 1. We're going to actually create a new entry in counts where the key is W and the value is 1. Now, a more elegant approach, I don't like this use of the word elegant, and I'll tell you why in a minute, but a more Pythonic approach, the way that Python programmers actually do this, is the line of code we see down here. So we say that counts W equals counts get, and we pass W and 0 plus 1. Okay, so how does this work? Well, if our word's already there, Well, we get the count that we already have and we bump it up by 1, and then we store it back where we got it. If in fact it's not found, we get a 0. We bump that up by 1, we get 1, we store it into counts. So what's interesting is that this single line of code does the same work as these multiple lines of code. Okay, is it easier to read? Not to the uninitiated, which is why I don't think that it is elegant. I think things that are truly elegant are easy to read, right? This is, I would say, more Pythonic. This is the way Python programmers actually do this. Okay, can you do it the top way? Yes, you can. Can you do it the bottom way? You certainly can. This is the way real Python people tend to do it, which is why we call it Pythonic. Okay? And again, why don't I think that the bottom code is elegant? Because I don't think that when you look at it visually, that it's easy to understand, unless you're an experienced Python programmer who knows this construct. Whereas the top, almost anybody can understand that. Okay, so this is the code. The lower code is the code that we're going to be using, but we could use either the upper code or the lower code. Okay, so what other tasks are we going to do? Well, we're going to do some text processing kind of rule of thumb tricks. Okay, one is we're going to convert the text to lowercase so that occurrences of Python with an initial capital will match Python all lowercase. Okay, this is a typical trick. We also want to eliminate punctuation, so Python exclamation matches Python without the exclamation. Okay, what happens is that words that get right up against the punctuation have a tendency to gum up. They appear to be different words when they're not. Okay. And of course, the other thing that we're going to need before we do all this is we're going to have to split the text document into a sequence of words. Okay, so these are all text processing kind of tricks or methods that we're going to include in our code. Okay, so get the words from a file. What's that going to look like? So we ask for a file name. We open that to read, and we read it. Now, what's kind of interesting here is that we've really done, what have we done? We've done two things on the same line. First, we opened the file, and we gave it the variable text for the file object. And then it turns out we can chain the read right on the back. Now, do I like that? No, I'm not particularly fond of it. It's certainly no faster. Okay, the code is no faster than if we put the read on the next line. If we said, if we saved the file object and then we went down and we did the read on the next line. So you could say this is a little more Pythonic because you will see Python programmers who like to chain together operations. But for me, I really don't favor it. I'd like to see the read on its own line. Okay, so what are we reading though? If we do a read method, we're going to get all the text in the file in one big blob. Okay, all right. So now in the variable text, we have a blob of text. So how do we shift it to lowercase? Well, we just call lower on the text blob. Okay. How do we get rid of the punctuation? Okay. So this is what we do. We're going to do a for in. So we say for ch, which must mean a character in a list of special characters. Okay. We say text equals text, replace that character with a space. Okay. And this is probably not the most efficient code ever written, but when you get done, you're going to have a value in a text, which is a blob of all the text, which has been shifted to lower, and then all of these special characters that are used for punctuation, they have all been turned into a space. So that there's still a position there, but it's a space and not a piece of punctuation. Okay? And now we're going to say that words, which is a list, okay, is going to get assigned text, and we're going to call it split on text, which is going to return a list of the words in that text blob. Okay, and what's it going to split on? It's going to split on spaces, which is why we use spaces to replace the punctuation, because it's not going to interfere with our word splitting. Okay? Okay, so now here's what we're going to do. We're going to loop through the words, which are in a list called words, to build the counts dictionary. So we're going to say counts equals an empty dictionary. Okay. And then we're going to say for W in words, okay, counts W. So when we use the word as a key, is going to be get. It counts with a W with a default value of 0. So again, here's what's going to happen. If we have already created an entry in counts for that word, then it's going to find it. We're going to retrieve its current count, and we're going to bump it up by 1, and we're going to store it right back where we found it. If we don't have an entry for that word yet, because it's the first time we encountered it, well, then we're going to get the value 0, because it's not going to be found. We're going to bump that up by 1. We're going to get 1, and we're going to store that 1 back into count. So this is where we create the first entry for that word. Okay? And I just want to point out, you might ask me, you may say, Kevin, why isn't this line indented? And I'm going to say that's a typo. Okay, this C for count should be right on top of the F for 4. Okay. So how could we print a list of words in alphabetical order with their associated counts? Okay. Now, I tell you the first thing I would do. If I were testing a program that had this code, the first thing I would do is I simply would print them out in whatever order they're in. Okay? I just like to see what the contents of the dictionary look like. Okay? Then I would worry about getting them in the right order in the output. Okay? So that's how I would write the program. Don't try to do too many things at the same time. So if we want to get a list of words that appear in the document, we could call that word unique words, and we could assign it list of the keys from counts. We call the keys method on counts and wrap that into a list. Okay, it looks okay. Put the list of words in alphabetical order. Well, if it's just a list of strings, we can sort it into alphabetical order by calling sort on it. Okay, that's fine. Print the words and associated counts. Okay, here's what we could say. So we could say for W in unique words, print W, and then we look up the count. Pretty nice, huh? Pretty nice indeed. This will probably not be useful for large documents with many words that appear only a few times. A more interesting analysis is to print out the counts for the n most frequent words in the document. So, some value, the 50 most frequent words, the 100 most frequent words, the 10 most frequent words. To do this, we'll need to create a list that is sorted by counts, most to fewest, and then select the first n items. Okay, so that's going to take some more post-processing. If we just want all the counts, well, we can do the code that we just saw here on slide 123. That'll work just fine. But if we need to take into consideration what the counts are and sort them first, well, that's going to take a little bit more work. So let's go find out how to do that. So we can start by getting a list of key value pairs using the items method for dictionaries. So we can say items equals create a list from calling the items method of count. Okay, so what we're going to get is we're going to get a list of tuples, key value pairs. Okay, so these key values, foo, bar, and spam, are computer science funny values. Okay, they're kind of arbitrary values. So these would be three entries from the list. This is an arbitrary word. This is an arbitrary word. This is an arbitrary word. Okay, so, and then what are their counts? Well, foo is, that happened 5, bar happened 7 times, and span happened 376. If we try to sort them with items dot sort, if we just call the sort method on this items list, they'll be ordered by components from left to right. The left components here are the words. That's just going to put them in alphabetical order. That's not what we want. Okay, so we're close to what we want, but we're not where we want to be. Let's go a little further. So that'll put it into alphabetical order, not what we wanted. To sort the item by frequencies, which is the second entry in the is the second part of the tuple, the value part of the tuple. We need a function that will take a pair and return the frequency. Okay, now this is actually pretty easy to do. Okay, so we define by frequency. Okay, it gets a pair and it returns a pair 1. Okay, now you probably are not going to be surprised when you find out that the way you count within a tuple is you start at 0. So if we wanted the one on the left, we would have said pair 0. Because we want the one on the right, we say pair 1. It's all that 0 counting stuff. Okay? So this is all. It doesn't even pay any attention at all to to what the meaning of these things are or anything. You're just going to get the second one back. Okay, so now what we can do is we can tell the sort that the key, this is a keyword parameter. We say the key is by freq. So that's the name. That's a non-conforming name of a function. Okay, that's not a proper function name. They should be in lowercase with underscores between the words. Oh, okay. But you will notice again that there's no set of parens that come after the end of the function name because we're not calling the function. We're actually passing the function to the sort. We're saying sort. Oh, when you want to call a function in order to tell how to sort these, call this a by freq function. Okay, so we're not calling it, we're passing it. So we're making progress here. What if we have multiple words with the same number of occurrences? We'd like them to print in alphabetical order. Oh boy, yeah, there's a problem. Now it turns out it's easier than you think. Okay. IT people have been sorting things for eons. Okay. Sort. Okay. And it turns out that they have a way of sorting things in by multiple fields. Okay. Now, one thing that we can do is this is a really simple way to do it. Let's go on to the next slide where it's going to tell us. Looking at the documentation for sort via help sort, it says this method performs a stable sort in place. What's a stable sort? What's in place mean? In place means that the method modifies the list that it is applied to rather than producing a new list. Well, yeah, that makes sense because lists are mutable. Stable means that equivalent items, equal keys, stay in the same relative position to each other as they were in the original list. Now, this takes a little bit of thinking, but if things go into the list in alphabetical order, okay, and then we sort them on the basis of this count that we have, okay, things that have equal counts, even though we're not sorting on count, they won't be taken out of their original order. So if so if we sort the list into alphabetical order before we sort it by count or frequency, then words that have the same frequency will appear in alphabetical order. That's a side effect of this being what we call a stable sort. Why do they stay in alphabetical order? Well, because we'll sort the whole list into alphabetical order first, okay? And the stable aspect of this means that for things that have equal counts or equal frequency, we will not have disturbed their alphabetical order. It's pretty neat. So how do we do that? Well, we just do two sorts. So we say this, we say items, sort, okay? We order the pairs alphabetically. Why? Well, because it's going to take the first of the values in the pairs, and it's going to sort on that. Okay, and then we say items, sort, key by freq. Okay, remember the function that helped us to sort by the frequency or the count. Reverse equal true. Okay. Well, what does that do? Well, it puts it in descending order by frequency. Okay. Pretty cool. Now we're ready to print a report of the n most frequent words. Here, the loop index I is used to get the next pair from the list of items. The pair is unpacked into its word unpack and count components. The word is then printed left justified in 15 spaces, followed by the count right justified in 5. What does that look like? So we say for I in range n, okay. So somebody would have had to give us that. So we might have prompted the user, well, how many values do you want to print? The top, how many? And maybe they said 20. Okay. So for I in range 20, we unpack items I into word and count. Now, this is a really interesting thing. In the past, when we had some things going on the right side, okay, like when we were reading multiple values off the same line of an input file, okay, we did a sort of a multiple assignment like this. And we knew, like, if we read two things, the first one would go to word, the second one would go to count. Why does that work? Well, it works because this thing that we read on the right side, if it has two things in, it's just a tuple. Okay, so this syntax is just the syntax for how to unpack a tuple. So this is a key value pair. The tuple has only got two entries. Okay, so we unpack the left one into word and the right one into count. Okay, so this is just a capability that we've seen from way back, I think, in chapter 1, or if not that, chapter 2. And it turns out that we've been using this all along without really even having thought about these tuple things along the way. And so we've got two values, 0 and 1. This is, the first one is left justified 15 characters, and the second one is right justified 5. And then we're going to use word and count to get the job done. And that's it. We don't see the output, but if we wanted to go find this sample program and run that, we could do it. Okay? So this is kind of a classic example of why we would use a dictionary. Okay? If we want to keep a whole bunch of counts and we don't want to define ahead of time what we're counting, like these words, well, then we can keep the counts in a dictionary. It works particularly well because the dictionary has key value pairs. The key works very well for the word, and the value works very well for the ints that we store in there. So that works just fine. Okay. Now, what other things could we do? Well, we could have a proper dictionary. We could have some kind of a lookup table in which we had the key and we had the value. Okay. So product number, product name. Okay. So we could create a dictionary where the key was product number and the value was the string that had the product name. Okay, so that would be a really nice way to look up product names. Okay, so just think about anything you'd want to look up. Okay, that you can kind of manipulate into a key value pair, okay, even if the value is complex in its own right. Like, for instance, if it's an instance of the student class, which has three subvalues, right? Even with that, we could have the key be maybe a student ID or maybe the name of the student, and then the value would be the an instance of the student class, a student object. So it's very, very flexible, very powerful, and this is just a first introduction to what to do with dictionaries. So that's it for chapter 11. I'm going to say bye. Bye bye.